Let's dive into this hidden world. This is our explainer on subsurface investigation, the absolutely critical mission engineers have to complete before a single ounce of concrete is ever poured. And this right here is the core principle. Before we build up, we must look down. The whole process is really a 5-stage mission, a journey that starts at the surface and goes all the way down to bedrock. It kicks off with reconnaissance, dives into detailed investigation, carries on right through the construction phase, and believe it or not, even continues long after the building is finished. This systematic journey is what makes sure the structures we rely on every day stand strong.
All right, first up is Stage 1. What we call Site Reconnaissance. Now you should think of this as the initial intelligence gathering phase. Before any heavy machinery shows up, engineers basically become detectives, scanning the entire landscape for clues that are hiding in plain sight.
You'd be amazed what the land itself can tell you. Engineers are out there studying the topography, looking for things like steep slopes that could be a problem. They're observing how water flows, looking for high flood marks that scream seasonal risk. They're even hunting for subtle signs of past landslides. Every one of these features is a critical piece of the puzzle, helping them build a first draft risk assessment.
But the detective work goes deeper, digging into history and even biology. Old maps or historical records might point to forgotten mine shafts, which are a huge collapse risk. And get this, even the local plant life can give you clues. Certain types of vegetation only grow in swampy, unstable soil. It's all about piecing together a complete picture of every potential hazard before you even think about breaking ground.
So now we move from just looking at the surface to a real hands-on investigation. Stages 2 and 3 are where engineers start physically probing the earth. This is where the core question shifts from a simple, can we build here, to a much more complex, okay, how exactly are we gonna build here?
And that brings us to the big question of Stage 2, the preliminary investigation. The goal here is pretty straightforward. Figure out if the project is even feasible at this spot. This means getting a rough idea of how deep the soil layers are and a general feel for the ground conditions, just to spot any immediate, show-stopping red flags.
One of the most direct and honestly coolest tools for this is the trial pit. It's exactly what it sounds like. They dig a pit, usually up to about 4 meters deep, that lets engineers literally see the soil layers with their own eyes. It's the perfect way to get a direct look at what's going on near the surface and to grab those first crucial soil samples. So, with feasibility confirmed, we move into Stage 3, the detailed investigation. This is where things get serious. The focus shifts to gathering super precise data. We need to know things like the soil's shear strength, which is just how well it resists being pushed sideways, its density, and exactly how much it's going to compress under the immense weight of the building. This is the hard data that drives the entire final foundation design. To get that data from deep underground, we need to make some holes, or boreholes. And there are 2 main ways to do it. Percussion drilling is kind of the brute force approach. It uses a heavy chisel to just hammer its way through tough stuff like boulders and gravel. On the other hand, you've got rotary drilling, which is way more versatile. It uses a rotating drill bit, and they pump in this stuff called bentonite slurry to keep the hole from collapsing. That makes it suitable for pretty much any type of ground you can imagine.
Okay, so you've got your borehole. Now, how do you actually test the soil way down there? Well, one of the most common methods is the Standard Penetration Test, or SPT. They lower a special sampler down to the depth they want to test, then a standard weight hammer drives it into the soil. The key measurement here is simple. They just count the number of blows it takes to drive it a certain distance. That one number gives them a powerful clue about the soil's density and strength.
But the SPT isn't the only tool in the toolbox, not by a long shot. Engineers have some really specialized gear. For super soft clays, which are tough to sample without ruining their structure, they use a Vane Shear test right there in the ground. If they need a continuous, real-time profile of the soil's resistance instead of just testing at intervals, the static cone test is the way to go. And to directly measure how the soil actually responds to pressure, they have something called a pressure meter test that inflates a membrane right inside the borehole. Each test gives them a unique piece of the puzzle.
Now, while all these field tests are going on, they're also collecting soil samples to take back to the lab. And this is a really critical distinction. You've got disturbed samples, which are fine for basic things like classification, but for the most important data, engineers need undisturbed samples. These are pulled out of the ground with extreme care to preserve the soil's natural structure, because that structure is everything. It determines the soil's true strength and exactly how it will behave under the massive weight of a building. And back in the lab, these samples start revealing their secrets. They run tests like Atterberg limits, which determine how the soil's consistency changes with water, from solid to plastic to liquid. Triaxial tests actually simulate the incredible pressures under a foundation to find its breaking point. And chemical analysis checks for anything corrosive that could eat away at the foundation over the decades. Every single test adds another layer of certainty to the design.
So, with the design all buttoned up, construction can finally begin. But, and you can probably guess where this is going, the investigation isn't over yet. Nope. Stages 4 and 5 are all about making sure our predictions match up with reality and guaranteeing the structure's safety for its entire life.
Stage 4 happens right in the thick of construction. As they're excavating the ground for the foundation, engineers are on site constantly checking that the subsoil conditions they're actually uncovering match what the boreholes predicted. If they find something unexpected, like a different type of soil or way more groundwater than they thought, they can adjust the foundation design right there on the fly to manage the risk. It's a non-negotiable reality check.
And finally, we get to stage 5, post-construction. The building is up, people are using it, but the job isn't done. This stage involves monitoring the structure for years, measuring for any tiny bit of settlement or tilting. This long-term data about how the foundation is actually behaving is priceless for judging its performance and figuring out if any strengthening might be needed decades down the road.
So after all this fieldwork, all this lab analysis, and all this monitoring, what do you get? Well, it all culminates in one of the most critical documents in any construction project, the investigation report.
This report is basically the bridge that connects all that data to the final design. It translates all the raw numbers and charts into clear, actionable advice. It gives specific recommendations for the foundation, like exactly how much weight the soil can safely hold, or the precise specs for any deep piles that might be needed. It is the final, authoritative word from the ground up, and it guides every single decision that comes after.